dive into these different sort of things. The first we're going to talk about is return codes. Okay? So I noted that there's classes of things that are fairly frequent. They're common occurrences. We may think of them as, in some sense, unusual or not the absolute typical case, not the case where we're focused or getting the work done, but in the bulk of the work. But they're things we have to handle. They mark the end of the work, for example. End of file, as an example. We're dealing with have you folks seen linked lists? Okay, so linked lists, so we have a list that kind of going through. So you have something like this. There's kind of a payload here, maybe it's a character, and then we have a link to the next item in the list, and we have another character there, and a link to the last item of the list, and maybe there's another character here, one, and then there's a distinguished end of list thing. These sort of data structure. This is an example of a data structure. Holds up sequence values, and it's really valuable because it's so flexible. You can kind of swap things out in the middle of the list, rearrange it, knock this guy out in the middle or what have you. And sometimes we iterate through these lists from one thing to the other. Maybe we're handling each thing in turn, saying, oh, it's an A, we got to do this. Oh, it's a B, we got to do that. Oh, it's a 1, we do this other thing. And eventually, ladies and gentlemen, we're going to hit the end of the list. We're going to get to the end of the list, and we're going to have to handle that case. Maybe it's not the case where we're doing most of the work. Maybe we're doing most of the work for each item in turn, but we do something different for that end case. And we have to be able to handle it. In other cases where we're looking something up in a data structure, we're saying, you'll see there's an example I give later in class of finding something in an array, or finding something in a binary tree, if that means anything useful, or finding something in a dictionary, which can kind of look up a value, and which is common in many, many languages and libraries. And if we're going to do that, maybe the thing we're looking up is not in there. Maybe, in fact, we're looking it up to find out if it is in there. And we need some way of sort of saying, hey, it ain't here. It ain't here. So we're going to return a distinguished value in these cases. These are all cases where as a result it's common. We want a lightweight mechanism that will allow us to encode these things. And so we return a code. Maybe we return a code, and the code is null for the case where we find something. Maybe the code is -1 for the case where we say, look up the index, in this array of characters, find me the index of the first occurrence of the letter Z. And it returns, Z is the first item, it returns 0. If Z is the third item, it returns 2, right? Suppose we look something up, and suppose we have an array and Z isn't there. That ain't there. We want to return something special, and we might return the return code -1. Why? Because that's something we can't get legitimately normally. It's an unusual value. It's a distinguished value. And as such, we can recognize it and say, oh, it wasn't there. Okay? That's helpful. Now we go on and reason about it. So, here, ladies and gentlemen, we are returning sort of standard values with a particular meaning associated with it. Distinguished examples of these sort of the typical types of values you return, but distinguished ones of those. You might have distinct return codes for things like there's been, the array is empty versus it's not in the array or something like that. You could do that. Okay, so why do we do this? Well, it turns out that it's lightweight. What I mean by that is it's very frugal in terms of computational power. It's very easy to implement. It runs really quickly. And this will be important when we come on to some of the other mechanisms, okay? What it means is you can do it very rapidly, you can do it frequently with very, very little adverse performance impact. In other words, your program can run, your generation probably doesn't say it, well, my generation didn't even. That can run lickety-split, okay? Quote me on that. So your program can run very, very quickly. It's also simple. It's a simple idea. We just return -1 if we don't find the thing. Otherwise, the values, well, they're indices into array, so they're 0, 1, or 2, or 3, or 4, or what have you. -1 means something good, right? It's kind of a conceptually simple idea that's simple to implement. There's not a lot of fancy mechanisms required. What are some disadvantages of this? Well, I turn it out to the crowd. What are the disadvantages of this? Yes, I know they stand behind me, but at least phrase in your own words.
You could still use the return value as a number. Like if it returns the index of the array, you might not check for an error value and then try and access.
Yes. Yes. It's exactly that. And I salute you. So this is the real risk here. We might get this value back and not realize that it was in any way distinguished, in any way unusual, in any way non-standard. So we squirrel away -1 as the index of z into this array. And then we use it later as if it's an array index, and we find that it blows up in our face. You know, we say, maybe we return this value back. We said, find element in some array, and we tried to look for something, some character C, right? And we assign that, I'll call it I by convention, so this is an index. But we don't even check. We're blithely ignore the fact that this could return something that's not a legitimate index. And later in our code, we actually look up in array, we say array of I, right? If this character is in the array, this is find element that it returns. If it is in the array, this will work just fine, right? If it's not in the array, then I is -1, and this will cause bad things to happen, folks. It may cause a bust or dump. It may cause you to have a crash in front of your eyes. Even worse, it may cause it not to crash. Why do I say that's even worse? You don't realize there's a problem. Maybe it fetches some value out of this that's actually not part of the array. It's located just before the array in memory or something, and it actually uses that value. And basically, you've got nonsensical things being computed. The user thinks it's all hunky-dory, and it's not. So in this case, ladies and gentlemen, the programmer is engaged in error and not being warned about it. If I may again use the term of some merit, but little seen these days, they are hornswaggling themselves. Okay? They are tricking themselves. This value has been returned as -1, but there's no checking going on that they handle it properly. No one's checking that they're cleaning up after themselves, that they're wiping their butt. Okay? For this awkward case. No one's checking they're dealing with this inconvenient case. And therefore, ladies and gentlemen, you may get a situation which works 99% of the times, and then the user enters something unexpected, like a name with an apostrophe in it, or with a dot in it, or something like that, and everything goes all to hell, and the program crashes, or worse yet, doesn't crash, we get the nonsensical data. Okay. So here we have a situation where return codes, because the handling is not enforced, they can hide errors. They can hide problems. Another issue is risk of inconsistency. So someone may treat a 0 as meaning success and a -1 as meaning failure. Someone else, if it's not clearly documented, not clearly described, may assume that quite the opposite. In one case, you may think 0 is success, the other person may think it's failure. If it just returns 0, and if the code is handling 0 in it, you see if it's equal to 0, double equal to 0, you're not sure what it means. Okay? So there's a risk of interpretation error or inconsistency between what the designer intended and what the person's interpreting it. And furthermore, ladies and gentlemen, there's no metadata captured here. So if you were trying to use this to signal something like a failure of a network connection or something like that, there's no data about where that occurred within the system that's being stored up, that's being passed on. Okay? No information about where this problem occurred, where the database failed to connect. Where did we fail to connect the database within the program? Was it in the place where it looks up people's names in the database, or was it in the place that charges, records that they in fact will be attending the event or something like that? Okay. So there's no sort of data about where in the program it happened. You heard this term metadata before? Okay, what is metadata? Data about data. Information about data. In this case, maybe you're passing up a code that says there's an error, and you'd really like to be able to say where on the floor that error occurred. You'd like to be able to say the error occurred on the floor, right? And there's no opportunity to do that. There's no opportunity to say the line number where it happened, which would be really nifty in some places because you could use it to go figure out exactly what resource failed or what have you. Okay? So here it's kind of a very small amount of information. Ladies and gentlemen, there's something that I wanted to present to you earlier. And let me be straightforward, I forgot. So I'd like to actually just give you one best practice, which you will see in C. So if you're comparing return code, like if you want to see if the return code for I indicates not found, we could say, something like I equals -1. We do this special thing, right? We throw up an error message to the user saying, measured and invalid code. Please choose a code between this and that, or something like that. We can do this, right? From something I have told you, what's a way that this would be approved? And based on this, oh, that's really, but I don't think you folks are interested in this lecture in the Coleman filter. Okay, so based on this here, what's something that could I just said equals -1 in my code? What does it stand for? The interpretation issue. So generally, with return codes, the best practice is to encode them with a constant. If we're dealing with C, we do a pound define up here, a pound define, not under bar found, or something like that. And then you could actually check if this equals not found. And not found is pound defined to be -1. Okay? Not under bar, and actually put it in parentheses. Why do I put it in parentheses? Why do I put that in parentheses? Yeah, so there's a risk if I didn't put in parentheses, it may say -1. So if someone had in their code 2 and right next to it not found or something like that, it could be a space between these. It would turn it into, if it didn't have the parentheses, it would turn it into what? 2 - 1, which isn't what was intended. You want to have this in parentheses to prevent any sort of weird interpretation based on the surrounding context. So we could say if I equals not found, do this, and this not found is just defined to be -1. So that's great, folks. But one of the most common error in C, one of the more common ones, is what? It involves equal signs. What would it be? Putting only one. So, ladies and gentlemen, if I left out the second equals, so instead of saying if I equals not found, if you instead said if I equals not found, what would happen? We assign the value. So what would happen is that the value of I is overwritten, clobbered by is another common term for it, the value of not found. In this case, it would evaluate to true, because -1 is actually true. It's 0, that's not true. And it would, in fact, execute this thing. And you might never know about it. But I has been changed by it, okay? Even if I was something different, maybe I was 3 here, but it's been overwritten by not found. Does this occur? You bet it occurs a great deal. So how do we, and this was the suggestion I wanted to give, how do we avoid that? Well, one way that folks identified decades back when I was a young man and just starting out my programming career was these professional C programmers, you instead of putting the variable on the left-hand side, you put not found, you put the constant you're testing its equality to on the left side. So we would have here something like this. If not found equals I, then do such and such. Why do this? Yeah, exactly. So if I forget the second equals, what happens? Okay, I get warned, right? Here, if I forgot the second equal, I get warned. Does the compiler say, oh, you're overwriting it? No, the C compiler is just going to say, you got it, coming right up. And you have a program full of bug, with a nasty bug that you didn't realize, which seems to work okay for many cases. And if you don't test it thoroughly, you're in trouble. Here, ladies and gentlemen, you get a warning by the compiler to say, hey, this doesn't make sense, go fix it. Go figure. And you have to go and you'll find where it sits. So, ladies and gentlemen, if you're comparing in C a value to a constant value to a value from a variable or from any so-called L value. This could be an array reference, array of I or whatever thing that could be assigned to which you could assign a value. Put the thing to which, put the constant on the left. It prevents these sort of errors from occurring. You fall into a habit of this, it becomes a convention, it becomes a practice within your group, and you can prevent a lot of errors. Take it from an old C program to spare you trouble. Bit of a digression, but I hope I've emphasized the risk of misinterpretation as well with -1. So, ladies and gentlemen, the best practices here, pound define in usual code. So, POF, for example, is pound define in C. OK is pound define for certain things to indicate, okay, I connected properly versus OK. You might have error, ERR encoded. So you could say, if you have a function that says connect to a database, it either returns OK or returns error. And you do a pound define, just like up here, OK to be one thing, error to be another thing, return it wrong. Okay? Now, ladies and gentlemen, C enjoys, C is a language that enjoys many virtues to recommend it. Guy Steele, towering figure in the landscape of languages, and one of the bigger drivers behind Java, commented that about different languages. He was talking about, I think, Java, Lisp, and C. And he analogized C to a banged up pickup truck. What they call in Canada, they don't call it down in the States, but they call it in Canada a beater truck. Your beater truck. Gets the work done. It's small, easy to work with, sort of lightweight, and you can do it with a quick convergent package. You don't want to build a giant system with it unless you have absolutely overriding needs because of performance considerations or something else. And even there, you're often better off going with a higher level language, which allows you to tap into really good algorithms. But C lacks some mechanisms that we come to depend on within our software engineering quite heavily, and that help us prevent errors. And one of them is the use of enums. Okay? So the idea behind an enum is we can specify enumerations. So we could say, for example, we have an enumeration of possible values. So enum, we could call them, return codes. Languages differ for the exact syntax. We could say return underbar codes, and we might have several of them. We might have, okay. Maybe these are connection codes. Okay, connect codes. One might be okay. One might be, DNS unresolved. So it couldn't figure out how to get to that machine. Another would be, connect refused or something like that. So connection refused. These are different things it might return, and it declares them as constants that could be returned from a function. And then when you have your function, you can actually say it returns a connect code. Okay, we call it connect. Instead of connect codes, we call it connect code. And so then if we have a function, connect, a function connect here, we could have it return connect, maybe it takes some arguments and so on, like a char star that, or in this case it would be Java, say a string to a machine name, and it would return and return code, okay? Return code. And this tells you the legitimate return codes that it can return. So you're not confusing -1 and 1. You're not going to add a return code to a 3 or something silly like that. It knows this is a single sort of thing. It can only hold these possible values. Full stop. Okay? And so then you have this sort of return an element to this enum, and it delineates very clearly what the legal values are, and moreover, you could in principle have mechanisms that will make sure that you test all of them, all of the possible values, and some compilers can do that for you. They can say, have you handled all the possible values here? Okay. And in fact, good practice has us build default cases, switch statements, etc. So without going into that, with language like Java and C++, you should realize there's more sophisticated options than undefined, options that will clearly specify the set of possible return codes that are legitimate, and conventions that make sure you handle all of them, okay, within your code. Okay, so in terms of best practices, always handling all values. If you have a switch statement, you do switch on the return code, and you have, how many people in here have seen switch statement? Okay, yeah. So you know what I mean. I mean, if you have a switch on some value B, you have a bunch of cases, right? Case, and you could have case okay, right? For this, and then, it does whatever. Case, DNS unavailable, etc. And then, by convention, you should always have the default case. And that handles, just in case there's some value you're not expecting, or that wasn't handled up here, what do you do? And maybe you present something to the user and say, something bad is happening, please put up. We're going to talk about how we can use other mechanisms like exceptions for that in just a minute. Okay, so these are sort of return code considerations. One, again, best practice that's come up in some contexts is to make the default value, like in C++, you make the default value. In C++, it treats, if you don't initialize it, it treats it as it's 0, unless you initialize it. So you make the 0 value what 0 corresponds to in this list. If you use 0, it corresponds to an illegal value. Okay? And you can kind of rule that out. That's the subtlety. I don't expect you to understand it, but the point is here, each of these values in C++ actually has an encoding that's an integer. 1, 2, 3. You can actually say what they are, and you can make 0 the default value. If you don't initialize the variable, you can make it illegal. It's something that's not a legal case, so that you know if you're seeing a value like this, it's from some initialized value. It's a value that's initialized. Okay. That's a subtlety. Some of you may pick that up. I don't expect that from everyone. Okay. Okay. So I've just talked about return codes. Really handy, ancient in their origins, and helpful in many cases, but potentially, for the reasons articulated by the gentleman in the back, they are potentially dangerous because there's no forcing us to handle them. There's this case here. If we get back to return code, maybe it's some distinguished value like -1. We don't even check it. And we use it as if it were a normal value. Boom. It blows up in our face. Maybe immediately, maybe months from now. Maybe after we've delivered the report to the client that now has to be totally revised. Okay, so return codes. I'm going to subsequently go on to exceptions, but before that, let me